introduce the speaker while people watching the live stream come in remotely. Yes, it's my great pleasure to introduce my friend Kevin Buzzard, who is very much a local speaker, right? He studied here in Cambridge, and in the first big proof meeting, he decided he would start formalizing mathematics. Probably he will tell us about this. And was a pioneer in formalizing sophisticated mathematics in Lean, and made a lot to attract probably many of you to this area with this enthusiastic communication. And for all this time, he's been dreaming of only one thing, formalizing the only proof he really cares about.
Any proof I know.
About since his PhD, and today is the day. So he's now finally doing it, and he will tell us how it's going.
Thank you, Patrick. So yeah, I'm just going to say a bunch of things that people have said already. Oh no, I'm not, because my clicker doesn't work. Oh, I can move slides. That's what I can do. Is that really? That's what my clicker does? Oh, there we go. Right, so there's a picture at the back. Now there's a picture at the front. I'm just going to start with. So thank you very much to the organisers. It's always an honour to speak at the Newton Institute. And I'm just going to start by flagging two other talks, which also took place in this room, both of which, it's not at all unreasonable to say, both of which changed my life. And the first one was, of course, Andrew Wiles's talk from June 1993, which was at the end of a 6-month programme on Langlandsy stuff, which had been running for 6 months, and I'd attended almost all of it. And then there was this sort of final conference at the end in June. And there was a week-long conference, and they asked Wiles to speak, and for some enigmatic reason, he said he would speak, but could he have 3 lectures, not 1? And said nothing about why. So the rumours were flying, and so people were. There was this rumour that he was going to prove Shimura Taniyama, which everybody knew implied Fermat's last theorem. And in fact, one of my friends went to the bookies and attempted to put a bet on Fermat's last theorem being proved in the next 10 years, and they got turned down. So he said he'd give 3 talks, but there was a problem in that I just met this girl, and this beautiful woman, and she was a doctor, doctors in those days worked like 90-hour weeks, but she got a week off, and it was exactly the week of the conference, and she wanted to go on holiday, and had invited me on holiday with her to Ireland, and I had to choose between 3 talks by Andrew Wiles. So she was on call the Sunday night before, so she had a weekend on call, so 36 hours straight of work, which finished at sort of 8 a.m. on the Monday morning, and then she went to sleep. So we couldn't leave until Monday evening, and so I could be in Cambridge for the first of these 3 talks. So I went to the first talk, and it was completely incomprehensible. It was all, he's introducing these revolutionary new ideas. They were completely over my head, so I just thought, stuff it, I'm not sticking out these other 2 talks. So I went off to Ireland with this woman, who I'm still with 32 years later. We've got 3 children. So it was definitely the right decision. And then, of course, on the Wednesday, he announced the proof, and on the Thursday, it was on the front pages of the papers. But by that stage, I was in rural Ireland, and I'd completely forgotten about the whole Fermat's last theorem thing. And I only found out when this is before mobile phones. I only found out when I got back to Cambridge a week later that Fermat's last theorem had been proved. But I certainly didn't regret skipping the talk, not least because, of course, the proof was wrong, right? That's the entire second lecture is completely irrelevant because it didn't work. The proof was discovered, the error was discovered in the refereeing process. And so fast forward to late 1994, when I was a fellow of Trinity, and I invited my advisor, Richard Taylor, Wiles' student and collaborator, to give a talk at the Cambridge Number Theory Seminar, which I was organising at that time, where he spoke about the correct proof. And so I was there for that one at least. So that was a talk I missed, and this is another talk I missed. Tom Hales' talk, the first talk of Big Proof 2017, another talk that took place in this room. And this is a slide from the talk. So I should say, Wiles's talk changed my life because suddenly my area was like the most fashionable area in mathematics. And I just walked into a job a few years later. Because I was the guy that understood a bunch of the maths behind Fermat's last theorem. So that's why that talk changed my life, because it basically got me a job. By 1998, when I was on the job market, Taylor and I generalised Wiles's R equals T theorem, so it applied to other modular forms, and I think I was a very reasonable-looking candidate for a permanent hire. So this is a slide from Hales' talk. So what happened here was I got hired by Imperial, and in 2016 they put me on the Introduction to Proof course, and I lectured it. I sort of followed the guy's lecture notes from the year before, and the first time I taught it. But then I thought I wanted to spice it up a bit. So I thought I would try introducing theorem provers to this Intro to Proof class. And I didn't really know where to start. All I knew was that they'd proved the odd order theorem in COC, or ROC as it's now called. So I spent 2 weeks trying to figure out how to use ROC, but all the documentation is for computer scientists. So I floundered around trying to prove the square root of 2 was irrational, that sort of thing. And then there was this conference I was far too late to register for, but the Newton Institute were ahead of the curve, right? This is pre-COVID, but they were live streaming and videoing talks, so I could actually watch the talk live from the comfort of my own shed. And I watched Hales give this first talk in Big Proof 2017, and he talked about his formalisation of 3D sphere packing. And I've just spent 2 weeks fiddling around trying to prove basic theorems about equivalence relations. And then he stuck this slide about the kind of things that one would need in order to formalise automorphic representation theory, which is a part of the Langlands program, which is my area. And having spent 2 weeks doing basic mathematics, I'm looking at this thinking, wouldn't it be much more fun to be formalising this stuff in a theorem prover? Because I hadn't quite internalised the fact that sort of none of this had been done in 2017. I mean, rings had been done, but and so I started, and then at the end somebody said, "Well, what system are you going to use?" And Hales just said, "Well, I'm in Pittsburgh, and there's this system called Lean, which is also based in Pittsburgh. So I propose using Lean." And I thought, well, I've never heard of that one, but I started playing with Lean, and I quickly ran into Jeremy Abigad's book, Theorem Proving in Lean, which was a book that I could actually read as a mathematician. And so I read it cover to cover 3 times, and each time I learned more. And then I just started on the first thing on the list. I started a club for undergraduates, and by December 2017, we'd formalised schemes, the first thing on the list. And I was super excited about this. We'd formalised the definition of a scheme. No one had ever done it before. I'd collaborated with 2 undergraduates, which I thought was super interesting. I'd never collaborated with undergraduates before. I was running around the department telling any algebraic geometer who cared to listen that I taught a computer what a scheme was, and none of them were remotely interested. There was like Paolo Cascini, who just just proved finite generation of canonical ring with Kausha Birkar, who just got a Fields Medal. It was like, Kevin, I knew what a scheme was when I was a PhD student. It's like, what are you making all the fuss about? But that did not put me off, because I was still convinced that this was the most exciting thing this was, I don't know. I just realised that I'd started at the wrong end. And so the next thing I did was I formalised the last thing on the list, which was vectoid spaces with Patrick, who independently had the same idea at the same time. And then suddenly it all took off, and then by 2022 I was giving a plenary lecture at the International Congress, something which if you'd told me in 2017, I would have just laughed at you. Again, this talk that also took place in this room, and that I also was not present at, absolutely clearly completely changed my mathematical career. So I very much thank the Newton Institute for these 2 talks, which have, in some sense, sort of the foundation of my my mathematical career to date. So here's what I'm going to talk about. So now I actually start the talk. So I'm going to talk about formalizing Fermat's last theorem, which is a really, really difficult problem in algebraic number theory. And the question is, so it's a big proof, so it's good for this conference. But the thing is, it's a really big proof, right? So the question is, how are we going to get up there? So, the naive idea, the naive question is, how are we going to climb the mountain? But it's not a real mountain. That's not an actual picture. This is an AI-generated picture, just to be clear. So because it's a virtual mountain, you don't actually have to climb it. All you have to do is make sure there's a route from the bottom to the top. So you can kind of like jump to an arbitrary point in the mountain and make sort of ladders at that point and jump around. And that's really good because the stuff at the bottom is really boring, so undergraduate level things. And the stuff at the top is the really interesting stuff that Wiles did. And the kind of mathematics I've been doing all my life as a researcher and the kind of stuff I want to engage with. So I can sort of jump straight to the top and make bits of ladders there, and then other people can do. I can go straight to the fun part, which is one of the nice things about it. So that's what I'm going to do. I'm going to formalize Fermat's last theorem starting at the top, and then of course the big question is, what's the actual point? And this is a good question. So I have a personal, my personal reason for wanting to formalize Fermat's last theorem. There's two, right? Firstly, it's a piece of mathematics I love. It was the piece of mathematics that got me a job. It was the piece of mathematics that I've been generalizing for my entire life in some sense, or working around and using the consequences of. And of course, the other personal reason is that I've got completely addicted to the software. It's now my favourite computer game, and I just want to wake up. I wake up every day wanting to play with the software, and so I've sort of, so that's the personal reason why I want to do it. Because as far as I'm concerned, it's a fun thing to do. But of course, that's not what gets you a grant, right? Just saying I want to do it because I think it's fun. So the way I marketed it was I said it will be of great benefit to the mathematics community because it will force us to type in a bunch of modern mathematical definitions. The big problem. So Fermat's last theorem is proved by using the Langlands philosophy, and the Langlands philosophy is a big trendy thing that lots of people are still writing papers about. And the big problem with Lean's mathematics library is that we can't state any of those theorems in Lean because we're just missing too many definitions. So that's one argument that you can make to funders, is that we're going to make Lean's maths library better, and at the end of it, we're going to be able to explain, questions of modern math. Fermat's last theorem is 30 years old, but we're going to be able to explain modern number theory to a computer. At least we're going to be able to state the kind of questions that my colleagues are working on. So that's one reason. And then there's the secret other reason that is there, but that I don't really ever talk about very much anymore because it tends not to go down very well with some people. And for example, with Michael Harris. But the secret other reason is that I personally, and not everybody shares this, let me absolutely stress, not everybody shares this opinion, I personally think Langlands is out of control. The system now is, somebody releases a 200-page paper, it goes up, it gets uploaded to archive, and then there's a Quanta article about it, talking about the latest breakthrough in Langlands, and this paper hasn't even been refereed yet. And I think that that's a little bit, I don't think that that's the way it should work. And I'm not entirely convinced that these gigantic 200-page papers, but like when I was doing Langlands in the 90s, the papers were not 200 pages long. So something has changed. And I'm not convinced these papers are being refereed carefully. And as I say, one of the reasons I started using theorem provers was I was refereeing some of these papers in the mid-2010s, and I would find mistakes. And these were written by people that were supposed to be experts, and I'm just thinking that somehow humans aren't as clever as they think they are. So this is just a personal paranoia I have about the current state of the Langlands program, which I thought I would openly air, given that I had this platform. But as I say, not everybody shares that, and it might just be the case that I'm sort of old and past it, and can no longer I'm no longer an expert in the area, and so I'm just sort of worried. What I'm really saying is that I can no longer understand my own area, and this is my reaction to that. So that might be what's going on. But as I say, 200-page paper after 200-page paper, I think it's just a bit weird. And so one reason for formalizing Fermat's last theorem is that the Langlands philosophy is supposed to imply Fermat's last theorem, and I just think that there's a good case for arguing, let's just check we've got that right. Let's just make sure, I'm convinced it's right, but let's just check. Because the process of formalization has uncovered errors in the literature, errors in 200-page papers that clearly nobody has read carefully. And the errors have all been fixable, but the errors are there, and I'm sure we'll discover more, because formalizing, it finds them. So that's why. Okay, so now onto the talk proper. So I got funding from EPSRC, part of UKRI, the same people that are funding this place. They bought out my teaching for 5 years, and I'm incredibly grateful to them, because I believe I'm doing something that's really important. And the job is, what people are quite confused about. Well, everyone thinks that I'm going to prove Fermat's last theorem, but if you actually read what I said I'd do, is I would reduce Fermat's last theorem to results which were known in the 1980s. That's what the proposal says, and that's what give me 5 years, and I'm confident that I can do that. But then there's more work to be done after that. So, as I say, the way I sold it is we're going to start at the top and we're going to come down. And one thing I particularly like about this strategy is that it gets computer scientists very nervous. They're just like, oh, we've seen catastrophes happen when people do that kind of thing, because then the things don't join up. But I'm just like, it's all right, we know what we're doing. I'm convinced that we know what we're doing. So we're coming down from the top, and then something is coming up from the bottom. That something at the minute is Lean's maths library, which is being manually written by humans. We now have a lot of an undergraduate degree, not all still not all, but most of an undergraduate degree. And then maybe later on we'll have AI auto-formalization, who knows. But something is coming up from the bottom, and we're coming down from the top, and then the idea is we meet in the middle. So that was how I sold the proposal to EPSRC. And now I'm trying to do it, and it turns out it's more complicated. So I'm going to talk something about what it looks like in practice. Let me tell you what the theorem looks like. So there was the paper that everyone says is the proof of the theorem. There was this big 100+ pages by Wiles. And then there was this error. So the error was removed from the 100+ page paper, and it was replaced by a reference to a second paper by Taylor and Wiles. So Taylor was my advisor, and Wiles was his advisor. So this is right. If my advisor's advisor, my advisor proved Fermat's last theorem, and his advisor proved Fermat's last theorem. So why can't I prove Fermat's last theorem? I think we should make it a British tradition, proving Fermat's last theorem. That's the reason. That's why I think we should prove Fermat's last theorem. So the paper is 120 pages in total, and even just the Wiles paper alone has got over 80 references. And so if you if you replace each reference by the proof of the relevant thing that's being referenced, if you write it out what does in full even mean? If you write it out in full, my guess is a couple of thousand pages. But what does in full mean? Right down to the axioms of mathematics? Well, that would be pointless because we already have most of an undergraduate degree. So why don't we just write it out up to sort of undergraduate level? Then my guess is it's a couple of thousand papers. So in contrast, the odd order theorem, that was about 300 pages plus some undergraduate level material. So maybe it's sort of 6 times as big as the odd order theorem proof, which took like 70 person years or something. So it's quite a big. And then the other thing is the proof of the odd order theorem is hundreds and hundreds and hundreds of lemmas about finite groups. Whereas the proof of this theorem is very different. the proof of Fermat's last theorem. This is one of the striking things about it. It's a statement in elementary number theory, but the proof uses results from all over pure mathematics, including areas that I'm not at all an expert in. For example, real analysis, that was my bogey subject at university. This is the topic I wanted to avoid, real analysis. And there's some non-trivial harmonic analysis that goes into this proof. And I've never read those, the harmonic. The harmonic analysis is input from a work of Langland's from the 1980s that I've never read and really have no intention of reading. Because I'm gonna skip, that's the part I'm gonna do last, right? If I get to the end before I die, then I'll be doing real analysis at the end. or hopefully persuading other people to do it for me. So as I say, I'm going to do the reduced to the 1980s bit, and that bit is stuff that I'm much happier with, but much more on the algebraic side. So it's arithmetic. That doesn't mean 2 add 2 is 4. Arithmetic is some technical. It means like Galois cohomology of global fields, and things like the class field theory. That's what number theorist means by arithmetic. So non-trivial theorems in number theory, commutative algebra, group theory, that kind of thing. Very much on the algebraic side of things. So that's what I'll be doing. So I want to say something to a non-expert audience about the difference between what Wiles did and what we're going to do. So just to give you some kind of, I'm not going to do too much on this because I know you're not experts, but let me just explain. So the thing we're not doing is just translating the Wiles paper. We're translating a modern version. This is another reason I'm doing it. Since I started using theorem provers, the way I think about mathematics has changed. And this was something that struck me. This was something I had no idea was going to happen. When I was reading technical papers in number theory before, the only question in my head was, does this argument work? Is this argument correct? Could it be broken down in theory to the axioms of mathematics? But when I started formalizing, basically for practical reasons as much as anything else, I started asking a different question, a much more Bourbaki-like question, which was, is this theorem being stated and proved in the correct generality? Is it being proved using the correct tools, and is it being framed in the right way? And that was not the kind of question I was interested in beforehand. But now I'm really interested in that because if you prove things in the correct way, then proofs can be maybe more modular, proofs can be, I don't know, it just seems to me, I've become sort of convinced this is the right way to think about things. And when I realised that this was the case, I thought it would be really nice to revisit the proof of Fermat's last theorem and read it in that new way. And just sort of to check that, as you type it into the machine, you start thinking, well, do I need this assumption? Why am I putting this assumption? It says that assumption in the papers, but do we actually need that assumption? Why is it there? So that's another reason that I'm interested in formalizing the proof, because I'd like to revisit it now I think about mathematics and this. Formalization has changed the way I think about mathematics. So let me explain the proof I'm formalizing. So you start with a counterexample. It's proof by contradiction. You start with a counterexample of Fermat's last theorem. I say that because the constructivists know that it isn't a proof by contradiction. So it's a proof by contradiction. You start with a counterexample of Fermat's last theorem. A to the p add b to the p is c to the p. And then you, so those are concrete numbers, and then you make this, then x, y are variables, and you make this random cubic equation in 2 variables. And that's called an elliptic curve. And El Gouache wrote it down first, but then Fry related it to, I don't know. So I don't quite know who to, most people call it the Fry curve. I'll call it the Fry curve. But props to El Gouache for writing it down first. So we write down this elliptic curve. And then the game is, and now by the Langland's program, elliptic curves and modular forms. Elliptic curves are algebraic things, modular forms are analytic things, and the miracle is they're related. So the game is to relate this elliptic curve to a modular form in some way. And this is the way Wiles did it. This completely novel strategy introduced in the 1990s. So in particular, this is something that we are going to have to engage with. If I'm going to reduce Fermat's last theorem to the 1980s, we can skip all of this, machinery they use, but this we're going to have to engage with. So the novel strategy that was introduced in 1993 was you choose some prime L, and then you find a modular form which isn't the right modular form, but it's the correct modulo L. You find a modular form which is congruent mod L to the correct modular form in some way. And now you've got something which is right mod L, and then you want to make something which is right modulo L squared. And so that could have been done in the 1980s. But then you want to make something which is congruent modulo L squared and L cubed, and then take a limit. And this is the big new thing that was in the paper. You prove a modularity lifting theorem, an R equals T theorem. And the R equals T theorem enables you to perturb this modular form, so it's right modulo L to the n for all n, and then you take some limit, and then you've got the right modular form. And so now you've got this. Now this elliptic curve is related to a modular form, and then you've got to somehow finish the job from there. You've got to now figure out why that's important. And like in the 80s, that was a huge shock to the world in the 1980s, that because this was a known conjecture from the 70s or the 60s even. Taniyama and Shimura and Vey as well all had this idea that elliptic curves and modular forms should be related. But the big shock, this theorem of Ribbit, was that this fact might imply Fermat's last theorem. So that's the strategy, and that was the strategy that Wiles came up with. And now the question is, what are we going to do? And so this is this part is a collaboration with Taylor, and the question is, what's the modern way of doing it? And so, Taylor and I collaborated, by which I mean he told me all the answers. I told him which bits I fancied doing in Lean and which bits would be nice to do in Lean, and then he told me which proof I should be formalizing. And he's very graciously just given a course about this proof in Stanford. So now we have a nice solid reference. And he's giving another course about it next semester. So he's not at all engaged with the Lean, but he's thought very hard about the modern way to prove Fermat's last theorem, and is currently thinking about that question. So we have a variant of the strategy, and the whole point is that it's not the original. It's not the we're going up the same mountain, but we're just taking slightly different routes up. We're diverging in places, but we're going to see much of the same scenery, basically, on the way. At the end of the day, the idea is, in the last 30 years, arguments have been generalized and simplified. So as a consequence, for example, we're going to end up proving that all elliptic curves over all totally real fields are potentially modular. So that's a statement that's stronger in Wiles proved that semi-stable elliptic curves over the rationals were modular, so a far smaller collection of elliptic curves, but a stronger conclusion. So we'll end up proving that, and one nice advantage of that is if you know that an elliptic curve is potentially modular, then you can meromorphically extend the L function. So one glorious conclusion of this multi-decade human year work is that we'll actually be able to state the Birch-Swinnerton-Dyer conjecture. That will be one of the glorious consequences, because the Birch-Swinnerton-Dyer conjecture is a statement about the value of the L function of an elliptic, the behaviour of the L function of an elliptic curve at the point 1. But the L function of an elliptic curve is defined by an infinite power series that only converges for the real part of S bigger than 1.5. And to meromorphically continue that function to the whole complex plane, you need 2,000 pages of work. So that will be one consequence, is that we'll be able to state one of the millennium problems. So there's the plan. That was what Wiles did, and now I'm just going to discuss the difference between what Wiles does and what we're going to do. So Wiles chose 3. He worked with the prime 3, and we're going to work with the prime p. So there you go. There's one difference. And the reason that we're choosing a different prime to Wiles is because the next step, you have to find a modular form which is right mod p, and Wiles found a modular form which was right mod p right mod 3 using the Langland's tunnel theorem, which stinks. Because it's very hard analysis. It involves like non-Galois cubic base change. It involves a lot of harmonic analysis, and that's my least favourite thing. So if we work with P, then we can avoid the Langland's tunnel theorem. So as far as I'm concerned, that's a big win. This strategy just minimises the amount of harmonic analysis. And it somehow, we save on the harmonic analysis and we don't lose. It's a win, right? We have to do other things, but overall this is a big win. So we have to use much less non-trivial analysis. But Weil's got this thing for free as a result of the Langland's tunnel theorem, whereas we have to do some work to get this modular form which is correct modulo P. And the work involves proving an R equals T theorem, but we were going to have to prove an R equals T theorem anyway. So we're going to prove an R equals T theorem, we're going to use it very early on, and then of course we use it again to go from the next step, to go from a modular form which is right mod P to a modular form which is right mod P to the n for all n. So we use, I've got to prove an R equals T theorem, so we may as well use it as much as possible. So you can see that this R equals T theorem, which I'm going to say more about later, is sort of becoming this central thing. It's clearly the thing that's holding everything together, and it's also something we've got to do because it wasn't known in the 1980s. So we're going to have to prove it, so we may as well use it lots. And then we've got to get the contradiction. Now the elliptic curve is related to a modular form. Where's the contradiction? And the funny thing is, it's a weird symmetry. To get the contradiction, Weil switched from 3 to P and invoked Ribot's theorem. And I would happily have formalised Ribot's theorem, but we don't need to do it because we're going to switch from P to 3. And so the 3, for some reason, it's the smallest prime, which isn't problematic. We're doing Langland's for GL2. And so 2 is somehow problematic. But 3 we can just about get away with. So we're going to switch to 3. And then we're going to have a 3-adic Galois representation which looks incredibly suspicious. It's unramified away from 2. It's sort of flat at 3 and unramified away from 2 and only very tamely ramified at 2. And it just looks like the kind of thing that couldn't possibly exist. But to prove that it doesn't exist, you deduce. You look at the 3 torsion, and you look at the number field cut out by this, and you look at the discriminant of that number field, and the discriminant is suspiciously small. And so now you need a theorem in the literature that says number fields have got large discriminants. And fortunately, that theorem was known in the 70s, the Odlyzko bound. So this is a result from analytic number theory, something which I know something about, but not very much. So we're going to use the Odlyzko. So Weil's didn't use the Odlyzko bounds, but I would far rather prove the Odlyzko bounds than the Langland's tunnel theorem because it's much, much easier. So what are these Odlyzko bounds? So let me show you. How does this work? So the Odlyzko bounds are something which I'm not going to do because they were known in the 1980s. Let's see if I've got internet. Yeah, I've got internet. So this is the Fermat's last theorem repo. So it's mostly lean code, but randomly in the middle of this lean code is a markdown file talking about assumptions. So this directory, this FLT/assumptions, is going to be stuff that I'm not going to prove. So this you can't read it because it's much too small. It doesn't matter what it says. But the idea is that the files in this directory, they're going to be axioms at this point. So let me just show you. Let me show you a file with an axiom. Let's bump this up so you can actually see it. So here's a lean file. There's not much lean in it. There's a long description. Of what this theorem says. There's a precise reference. There's a PDF. There's a GitHub issue number. This was proved in 1976. And at the very bottom, there's a theorem. Well, there's something which is a theorem in mathematics, but not a theorem in lean. And I'm stating it as an axiom. So that's what, in 5 years' time, this is the vision, or at least it was originally the vision, is that when you compile the proof, it will say, I proved the theorem modulo a bunch of axioms, And so this is something which I'm not going to be working on in the next 5 years. But if other people want to work on it, that's absolutely fine by me. They should let me know on the GitHub issues page. So this says if I've got a totally complex number field of degree at least 18 over the rationals, then I claim its discriminant is at least 8.25 times its dimension. And as I say, this is proved by Disco using a careful analysis of sort of zeros of the Riemann zeta function and generalized Dirichlet functions. And someone will have to do it if we're going this way. But as I say, we'd rather be doing this than Langland's tunnel, I think. And then we can go back, there's another, I've formalized another axiom. Here's another one, Mazur's theorem. That just says, it says, given an elliptic curve over the rationals, I claim its torsion subgroup has got size at most 16. So this is a paper from 1978, I think, by Mazur. So again, known in the 80s, over 100 pages. I'm just going to skip it, right, at this point. So we're skipping a bunch of stuff, but we're writing down axioms. And then, of course, the other question is, why haven't I written down more axioms? And the reason I haven't written down more axioms is because we can't even state those axioms yet. This is a recurring theme. We don't have the machine. Well, we don't have automorphic forms yet, and so it's difficult to state a lot of these axioms. We're going to need cyclic base change, but I can't state cyclic base change. We're going to need the Jacquet-Langlands correspondence, but I can't state. We're not even ready to state these things. How do Macs work? I've only just got a Mac. Have I got a? I had a talk somewhere. How does this? Oh, there it is. Great. So that was what I said I'd do: reduce Fermat's last theorem to stuff known in the 1980s. And as I say, my vision at the time was that we'd have 10 axioms. Or at most 10 axioms. I don't quite know how many axioms. Some of the axioms you use in the proof of other axioms, so you don't even need. We'll have some small number of axioms, and the idea is we'll have a sorry-free proof of Fermat's last theorem, but it will assume, 5 to 10 random axioms in mathematics, which will then be someone else's problem, or my problem if I get 5 more years of teaching. But it will be. Clearly we would have made progress. That's the point. We'll now, instead of one problem, we'll have lots more problems. But they'll be a little bit easier. And as I say, the one big, I can't even state them. We're working on this, but I can't even state some of these axioms yet. And I'm scared. Mario's told me not to be scared, but I'm scared of sorrying data. So I could state the axiom and I could just sorry all the data, and then it's like great, it's syntactically correct, but you can't start proving it because the data is not there. So that was the plan. I worked down from the top, other people worked down from the bottom, and then we get going. And so now we tried to actually do this, starting last October. But the problem is, we want to reduce Fermat's last theorem to some fancy modern statement that involves things that we haven't got definitions of, and then you can't begin to work on that statement because the definitions are missing. And then you kind of think, well, these definitions should probably be in MATLib, and then you put your Bourbaki hat on, and then you're like, okay, so now we want to write these definitions in the correct way and develop the basic API, and all of a sudden, you're working down at the bottom. You fell off. You're up at the top trying to do non-trivial things, but there's missing data, and so basically you have to come down for air, is what's going on. So we find ourselves at the bottom, and somehow for the rest of the talk, I'm going to illustrate how that's happening and how annoying it is by talking about the one thing. Where do we start with this thing? A really good place to start is with the R equals T theorem, because we know that we are going to have to actually prove an R equals T theorem. We're going to have to prove that a deformation ring is isomorphic to a Hecker algebra, because that was not known in the 1980s, because nobody knew how to do it. You could state the question in the 1980s, but nobody could prove it. So now we're going to do R equals T. So it needs to be done because it wasn't known already. So let me tell you what an R equals T theorem looks like, and then you'll see why I'm struggling to stay at the top of that mountain. So there's a thing called rho, and it doesn't matter what rho is, but rho is a thing. And then we're going to deform rho. This is how the proof works. So the first thing you attach to rho is a commutative ring called R, which is the universal deformation ring of rho. Okay, so it's a ring that has some universal property, and it's parameterizing all the ways that you can move rho. So this is a brilliant idea of Maser's. Deformation theory is something that was born in geometry. It was Maser's brilliant idea that it could be applied to arithmetic. So we're going to move rho around and take the maximal way of moving rho around, and that's somehow captured by a commutative ring called R. And then there's another commutative ring called T, which is a Hecker algebra, and you're supposed to think about T as the universal modular deformation. So some deformations are modular, they come from modular forms. So R is all of the deformations, and T is all of the modular deformations. And then, really they're representing functors. And the fact that they're representing functors, the fact that every deformation is a modular deformation, the clue is in the names. Every deformation is a modular deformation. And what does that translate to? That translates to there's a map from R to T. And basically, there's a map from R to T, and it's surjective because every modular deformation is a deformation. But it might not be injective, and in the kernel of that map is all the deformations which aren't modular deformations. All the elliptic curves that don't come from modular forms. They're going to be in the kernel of that map. And so the game is to prove that that map is actually not just a surjection, to prove that map's an isomorphism. Because then you know that every deformation is a modular deformation, and the elliptic curve gives a deformation. So the deformation is modular, so the elliptic curve comes from modular form. So that's what an R equals T theorem is. But you can forget about all that now, because this is what we need to remember. There's a commutative ring called R that we need to define. There's a commutative ring called T that we need to define. There's a map, a ring homomorphism from R to T, which we need to define. And then the big theorem is that map's an isomorphism. Right? And this has to be done. And this is where I started, right? So this is what I've been doing since October, thinking about that picture there. How are we going to do that? The definitions of R and T were known in the 1980s, so we could skip them. But the thing is, if we skip the definitions, we still have to prove the theorems, and you can't prove theorems about a definition that isn't there, right? We could state the theorems, but these are the theorems that we actually have to prove. So we cannot skip we have to make these definitions of R and T. We have to define R. We have to define T. We could skip them, sure, but then we're instantly stuck because then we can't prove anything. So we have to define R and T and F, even though they were done in the 1980s. We have to write down the definitions in there. Okay. So there's the 4 things we've got to do. Definitely we have to do those things by 2029. So let me start with step 4. How are we going to prove that F is an isomorphism? So this is how Wiles did it. So R is a fancy ring and T is a fancy ring, and F is this map. But what Wiles did was he came up with a purely commutative algebra criterion for a surjection between any ring. So now let R and T be any rings, and let F be any ring homomorphism from R to T. And what's in the paper is a crappy theorem in commutative algebra. It says if R satisfies a load of ring theoretic properties, and if T satisfies a load of other ring theoretic properties, and if F satisfies a load of properties, then F is an isomorphism. Right? So this is nothing to do with the actual application. This is the heart of the matter, a theorem purely in commutative algebra. And if there's one thing that Lean is good at, it's commutative algebra. And here you see we don't need to define deformation rings and Hecker algebras. This is just an abstract theorem about commutative rings. So this has been completely done. So that's as of about a month ago by my PhD student Andrew Yang, who's here today. So that's a great start. So we have the abstract commutative algebra theorem. Great. So that's not the end of step 4, but it is a great start. So what have we done with this abstract commutative algebra theorem? We've reduced question 4 to question 4 primed, which is to check that the hypotheses of Wales's commutative algebra theorem actually hold for the R we're interested in, and the T we're interested in, and the F we're interested in. And now you see, now we're stuck, right? We can't prove these hypotheses because now we need the definitions, right? So now we're forced to define R, T, and F. And so now we have to go down the mountain, right? We have to go back to the bottom and actually make this, even though it's been known for donkey's years, we have to go down and talk about R, T, and F, even though they were all known in the 1980s. Because we have to prove theorems about them, and we can't prove theorems about them if we don't have the definitions. So how is R defined? R is defined by you write down a functor, and then you prove that the functor is representable. The functor is from a certain category of rings, and then you prove the functor is representable by a ring, and then you say let R be the representing object. So now we've got to define a functor. We've got to define the relevant category, and we've got pseudo-compact rings, and then we've got to define the deformation functor. And the deformation functor is super, super complicated. It involves a huge amount of machinery, some of which we just about got in MATLib. Decomposition and inertia groups we have. We don't quite have local fields yet, which is kind of a pain. And finite flat group schemes is being developed in the toric project. Are there toric people here? I think Babik was here. Yeah, Michal's here. So there's another project doing something totally different in algebraic geometry, but they're developing the theory of group schemes. So that's wonderful. So that gave us finite flat group schemes. And so last week, Andrew again defined the functor. And so we sorted the theorem that it's representable, and we can do that, right? That's the data. This is all the data. So this was a huge amount of work making all of these fancy definitions, and then we can define the functor, and that's all the data done. And then the big theorem is that the functor is representable, and then we skip that because we can skip theorems because that was done in the 1980s. So that's great. So we can skip that, and now we get R. I mean, non-constructively, obviously, but I don't care about. Non-constructive is fine. The only facts we will use about R are the fact that it represents the functor, right? We have to check lots of theorems about R, but every theorem about R translates into a theorem about the functor. So who cares that the representation? Who cares that the construction of R is completely non-computable? So there's R. So we have R, and we've made great progress with 4, and we've done 1, all thanks to Andrew. So that's one way of getting Fermat's last theorem done, is that you get a PhD student to do it for you. But that's not the only way to get Fermat's last theorem done. Another way is to persuade the community to do the work for you. And so Andrew did R, so I had to do something. So I thought I'd do T, and the way I do it is by tricking other people to do it for me. So T is a subalgebra of an endomorphism algebra of a space of automorphic forms for totally different. So again, you see, just list buzzword after buzzword after buzzword, very little of which we have in Lee. So like 6 months ago, I defined totally real fields. 4 months ago, I defined totally definite. Well, Edison helped with. Edison has been developing. Someone who's about to be my PhD student has been developing the theory of central simple algebras. So, 4 months ago we had totally definite quaternion algebras, and about 3 months ago we had automorphic forms. So all of these things were slowly defined by me, and then to get the map F, we need to check that T is in the right. We're going to get the map F by saying, well, F represents a functor, and we're going to apply, what it means for a functor to be representable to get F, but that boils down to checking that T is in the right category. Because R is representing a functor from a certain category of rings, but it's not all rings. It's pseudo-compact rings. So we need to check that T is pseudo-compact, and it will suffice to prove that T is Noetherian. And here is where I made a mistake. I think a strategic mistake. So we need to show that T is Noetherian, and once we have that T is Noetherian, which boils down to some finite dimensionality statement, for spaces and modular forms that was known in the 1980s. But the thing is, I'd got engaged with this problem of T. So we built all these definitions from the ground up, And then we've got to prove this. So we built these definitions from the ground up, and then we've got to prove this finiteness statement about T to get F. And we used this amazing software by Patrick, where here the way it works is I need a bunch of lean theorems proved. And so the trick is I write the proofs in LaTeX, and then I throw them out to the community, and I say, here's a bunch of theorems. Here's a bunch of theorems. The statements are in lean. The proofs are in LaTeX. Now you go and do my job for me. This is the plan, and it works. So here's the. Let me show you it working. Let's do this. So there's all the LaTeX. So there's loads of LaTeX, and there's the Hecker algebra project. It's just like lots and lots. This is all written in LaTeX, and it depends on all these earlier projects as well. So we developed all the theory of Adels. Adels are fundamental objects in algebraic number theory. They're needed in Tate's thesis. We needed Adels, and so I just instinctively started writing Adels the way Bourbaki would have written Adels, because the idea was get it all into MATLib. So I made the definition, and then we had to make loads of API, and we've got all the, you can look at these theorems, like that theorem doesn't have a tick, right? That needs doing. Whereas you see, some of these theorems have got ticks. So you get a ticket, it's being done. And then you can look at the graphs of things. There's a small part of the graph of Fermat's last theorem. So I've got some projects just have one graph, and then we've got loads of graphs. So there's another one there. So that's one that William Core. So that I just gave to one PhD student, not my PhD student. I gave it to someone else's PhD student. I said, can you prove that these sides of this double coset space is finite? And in fact, they made a PR on Friday that I didn't have time to review, but some more of it. Blue means statement is done, proof isn't done, and green means statement is done and proof is done. So more of those blue things should be green, but I didn't review the PR. So this one is nearly done, and then others are much bigger, and this is in progress. Dark green means done, and all the prerequisites are done as well. So I throw this out to the world. What do? I go up, and then I go right, and then there we go. And this is what it looks like when I throw it out into the world. We have a project dashboard. So there's a list of things. So this is the stuff that's been, like 69 tasks have been completed. These are all the things that are done. At the beginning, these are the tasks that I've stated the theorem in lean, but nobody's said they'll do it yet. And these are the things I've stated the theorem in lean, and somebody has said they'll do it. And these are the things where I've stated the theorem in lean, and someone said they're actually in the process of doing it. And these are the ones where I've stated the theorem in lean, and someone has said they'll do it, and they've actually done it, and they've made a pull request. And then once I review the pull request, it moves into that one. So that's the workflow, this GitHub project workflow. And it works really well. So a few weeks ago, I put 10 new tasks up there, and it's like, now there's like 15 unclaimed tasks, and then a few days later there's 10, and then a few days later there's 5. And then a few days after that, there's a bunch of pull requests to review. And this is the clever thing about it, is that you don't have to be an expert in Fermat's last theorem to do one of these tasks. You just have to be able to read the task, read the LaTeX proof, and translate it into lean. And some of these tasks are about measure theory. So people come along who I've never even met, but they know something about measure theory, and they just do the task. And as I say, and it's amazing. So there's people doing algebra, there's people doing analysis. Everyone's working towards this common goal. This is what the Blueprint software enables. And as I say, it works. And it's been great. It's great fun doing it like this. It's really good fun. And there's people I've never met online. There's never met in real life, but they're collaborating with me online. And we're going to have a completely sorry-free proof of this finiteness result. We're going to prove that T is an Arthurian. We're going to have a complete no assumptions. It's going to be a complete sorry-free proof of this Arthurian result, and that will be that will be something that will be worth writing, because the finiteness result. Maria and Esh we have a proof the class group of a number field is finite, but Maria and Esh de Frutos Fernandez a couple of years ago reinterpreted the class group as a quotient of as an adelic group, and so modulo her work. Well, given her work, we can now give another proof that this thing is finite. We have a much more general finiteness result. And this will be a joint paper with whoever, all those people and whoever else joins in. We'll just write something. I'm going to have a proof that T is Noetherian. And now sort of stepping back, I'm just thinking, that's great, we've done that thing, but actually that took like months. That took like 5 months. And I didn't have to do it. And it's sort of only dawning on me now. I had to define T, but I didn't have to prove that it was Noetherian because I could have given a reference for that. But I just sort of got carried away. I was just like, this is great. We're doing everything in the Bourbaki way. I know exactly how to do it. I've got a really nice plan for the proof. Let's do the proof. Oh, look, it's 5 months later. And I don't think that I can do it. I don't think I can prove Fermat's last theorem at that speed. We could have just skipped the whole thing. We needed to define T, but I'd done that a while ago. We could have just skipped all the proofs. So I've realised now that actually we're not going to do it in 5 years if I keep doing it like that. So this is last but one slide. So I want to go more quickly, and it's clear what the next job is. So when we finish this work, we're going to have the map from R to T. And then the next big job is to check that that map, R and T in the map, satisfy a shed load of assumptions, just a big pile of assumptions. And some of those checks were known in the 1980s, and some of them were not strictly speaking known in the 1980s, but are very easy to reduce to theories that were known in the 1980s. And I'm not going to fall into that trap again. I'm not going to write a big LaTeX proof explaining how to do it. Because all the definitions are there now. We're just going to have like 10 really concrete theorems about R and T. And the moment they're reduced to the 1980s, I'm just going to skip them. And so I think in a few years' time, we might have a proof of Fermat's last theorem modulo things that were known in the 1980s. But those things that are known in the 1980s aren't going to be a list of 10 axioms. They're going to be a list of 10 axioms and like 100 other sorries, which are just things that we didn't get around to doing yet. So that's what I'm going to go for now. That's where we're going to go. And I think that will be nice because that will force me to actually write the general structure of the proof down. Then we'll really see what the proof looks like. But, you know, and I think we will finish this within 5 years. But it won't be the thing I originally had in mind, Fermat's last theorem as a consequence of 10 axioms. It will be Fermat's last theorem as a consequence of 10 axioms and 100 other things that we didn't get around to doing yet, but which were known in the 1980s. And then we will just slowly start knocking those things off. So I want to finish, this is the last slide. The one thing that's making me keep coming down to the bottom is because we're missing definitions, right? I can skip theorems that were known in the 1980s, but I can't skip definitions. So there's just a list of definitions that we don't have in MATLib yet, but that we're going to need in order to prove Fermat's last theorem. And we have to figure out how to get these things into the software somehow. And as I say, some of them, like classical de Rham cohomology, there was a plan proposed by Yuri Kudryashov over 2 years ago, and it's still not there, and we need it. And it's not entirely clear to me how we're going to get those things in. But for me, these are beginning to represent the bottleneck. So that's where we are. Thank you very much for your attention.
Thank you very much, Kevin. So, do we have questions for Kevin? Yes.
Myself?
Yeah.
Yeah. Hi. Do you worry that if you sort of go down and do the bare minimum definitions and all theorems, that you'll rack up technical debt from not having built out the API and therefore not having a great definition?
Yeah, maybe. Yeah, but I think, yeah. But I still think that I can sell, so at the end I'll be able to say, theoretically I've done what you told me to do, actually it's a bit crap. But yeah, that might happen. We shall see.
Fair enough.
But I need to do what I said I'd do.
Yeah.
Have you, so I mean, you're presenting a bunch of definitions here. Have you, like, are you going to write a blueprint for that? Like, I mean, it seems
Now, I'm
like
just going to pester people to do it. I can't write the blueprint. My impression is that Yuri understands how to do Durham cohomology much better than me. I need the hive mind to write that blueprint. I'm not sure. I mean, Amelia, my PhD student Amelia is doing Amelia has done group homology and take cohomology are on the gigantic PRQ. And continuous cohomology is Andrew's work, and that's also on the PRQ. And local fields is Maria and Esh's work, and that's not even on the PRQ, but it's coming. It's not on the PRQ because she's got to worry about her talk tomorrow. So like there are progress in these things, it's just that everything is sluggish because we've got 1,500 open PRs.
So I mean, clearly delegation is a major part of this, right? Like this is a big project. You need a lot of collaborators and contributors.
Okay. Whoever's watching, do this. Will that do?
Yeah, well, pointing to references, for instance.
Okay.
Like, read this book, and then you'll know what a moduli space is.
Okay, great.
Another question? Yes, Ken?
Can I ask a sort of
Hello.
very naive question of someone who doesn't formalise? It's just really, what is it that makes it hard to formalise definitions? In real maths, as humans, we sort of often, at any rate, to present with a definition, someone just writes down the definition.
Yeah.
Obviously, you're talking about things where the definition depends on something existing as a result of some non-trivial theorem, something like that.
That can happen, yeah. The other problem is people want it to work in the right generality. So you can't copy down what it says, Our definition of manifold allows like Banach manifolds and manifolds with corners and manifolds with boundary, because that's what Bourbaki would have done apparently.
You couldn't just sort of take a shortcut there, just not.
Well, I mean, I might do, yeah. I might cheat. But if you want them in MATLib, I mean, I sold the project as like, we're going to get great new definitions in MATLib, and if we instead we write crappy definitions in the FLT project, then I kind of feel I've done a disservice to the community.
I'd like to ask a very stupid question. Is it possible to prove formally that it is impossible to prove Fermat theorem from school algebra, from high school
Oh, I
algebra?
have no idea about that.
Yeah,
Yeah, maybe Fermat had a symbol proof, right?
We are harassed a lot by amateurs who claim.
Yeah.
You know.
Yeah, I don't think it is possible to do that.
Yeah,
You should ask a logician.
Yes.
I think maybe it is possible to, maybe a logician would say, actually, it's completely possible to do it like that. If you can prove it using this fancy stuff, then you can prove it. I think it might even be possible to do it. It just might take 1,000,000 pages.
I've got two little questions. So first, you said you didn't want to do any harmonic analysis, but you're happy to delegate. I mean, why didn't you simply ask Floris and Jeremy Tan?
They're doing other harmonic analysis. I did ask Manuel Ebel. I said, you need to switch from Isabel and prove the stable trace formula for me. But he wouldn't bite. I've got to find the right people. I'm sort of waiting until I can actually state problems. But it won't be long.
I was wondering, within your program, have you had encounters, or do you think that you will encounter a point that's basically you need to invent a new mathematical machinery to fill the gap?
No.
No.
It's all there. It's all there.
And maybe one last comment about the storing data. So, I mean, there is a story you know very well from the liquid tensor experiment where Johan Komlin wanted to have this Brindling resolution, and this is data, right? This is the resolution, and he simply started saying, here are the properties I need this data to satisfy, and those will become axiom. And it turned out that those properties were much weaker than having an actual Brindling resolution, and then it simplified just condensed mathematics.
Yeah, that was storing data turned out to be a massive win.
Yes, so what's your comment about that?
Yeah. I mean, yeah, you're telling me that, yeah. We need this stuff for lots of reasons, right? You want Durham cohomology, right? I think that great, if I can get away with not having Durham cohomology, I think we're doing the community a disservice if we try and dodge this stuff. So I think we should use this as an excuse to get it.
I think it's time for coffee break, so you can ask more questions.
I'll be here all week.
The coffee break.